So welcome to lecture 5. So the plan for today is to finish up some of the things that I didn't get a chance to talk about last time on just wrapping up the data collection polling module. And then we're going to start on recommendation systems today. If my clicker works. Okay, cool. Okay, so as a quick summary of the data collection module, first we started out with measurement, sort of a quick primer on measurement theory. And so what is measurement error? It's that there's a discrepancy, there's a difference between the construct that you care about and the measurement that you have, the quantitative measure that you have. Then we talked about selection and differential non-response. And this happens basically everywhere that you're collecting opinions from people. So today we're going to talk about recommendation systems and sort of a lifeblood of recommendation, or they were at least 15 years ago, of recommendation systems were explicit ratings from people. But because of, like very difficult challenges in getting explicit ratings from people, recommendation systems have mostly moved toward implicit data collection. But even there, you have similar selection effects on what type of data you receive. And then we talked about using stratification and weighting to mitigate these things when you have known covariates. And then finally, when you have these effects on sort of based on unknown covariates, so some some abstract concept called social trust, for example, that could affect both polling responses and who they support, then there's like very little you can do to correct your estimate. But what you can do is you can try to create bounds on what how bad your estimate can be from the ground truth. And what I want to emphasize here, and what's going to be useful going forward for the rest of the class, even when we're not thinking about polling at all, is you should never take the data that you have, especially data on human opinions, at face value. You should always ask, what did I measure, or what do I have a measurement of, and what is it that I actually care about? You should always ask who actually answered, who's the data available from, and how am I going to use it, and does who answered match the population that I actually care about that I'm going to deploy this system with? And sort of more generally is always try to connect what you're going to do with the data, do with your trained model, and how that connects to the data collection. So if you're depending on what you do, you might need to change what data you're collecting. You might need to change your measurement. You might need to change who you're asking from, or how you're weighting it, or how you're analyzing it. And sort of, I really do not want you to think about these things as separate concepts. Sort of when you have a job as a data scientist, you really can't just be like, okay, it's someone else's job to collect the data, and now I have like a nice table, somewhere in SQL, and my job is just to analyze that data. Like that's just not going to work in systems with people. Even if it's not literally your job to go out and collect the data, you need to understand how that data was collected. You need to sort of become best friends with the person who is collecting that data. And these ideas sort of, in some sense, the polling module is separate from the rest of the course, in that there's very few like machine learning models you trained, except unless you did the MRP part, or unless you're doing the MRP part of the homework. But that doesn't mean these ideas aren't intimately connected to what we're going to talk about in the rest of the course. Sort of everything that we talked about here, and you'll see this in a little bit with recommendations, are going to come up repeatedly. And even if I don't explicitly connect it, sort of you need to be thinking about this when you're doing the homeworks and you're doing the class project. Are there any questions about this module before we move on to recommendation systems? Yeah, so the question is how should we think about the difference between selection bias and differential non-response. So I would say that differential non-response is just a type of selection bias. So selection bias refers to like a very general phenomenon that sort of in all types of data, and like in observational data and data that you explicitly collect from experiments and all, like sort of it can occur everywhere. Differential non-response is a particular kind of selection bias that sort of that people use that term in survey collection. Yeah, so they're not like different concepts in some sense. Are there any other questions here?
How should we view the difference between someone who refuses to give an opinion versus someone that doesn't have an opinion?
That's a really great question. So the question is how should we view the difference as someone who refuses to give an opinion and someone who doesn't have an opinion? So we certainly see this in like political polling all the time, where sort of if you don't have people often add this like third or fourth choice, like don't know or not sure, and so it's like that's trying to tease it apart. It's like trying to give people an out for which sort of if they don't want to answer, or like if they can't answer that binary question. You often see this in ratings or recommendations all the time as well, and that's sort of there's no general answer, but like certainly they're very different. And what I would think about is exactly what I set up here, which is if usually that difference matters for what you're going to do, right? So like if you're doing like political advertising or like get out the vote campaigns, someone who doesn't have an opinion yet is very different. It might be a target for a persuasion campaign. Someone who has an opinion they're not telling you might not be a target for a persuasion campaign. So it certainly matters for what you're going to do. And so in different contexts, sort of if it matters, you should be like you should try to tease that apart in your data collection. And it might be hard to tease that apart. Any other questions? Okay, cool. Okay, so today is going to be then day one of recommendation systems. So I would think about this module as two parts. Even though I promised you that this class would not be about prediction, sort of I can't talk about recommendation systems without talking a little bit about prediction, just in case. Like I imagine most of you have not sort of encountered like the nitty-gritty bolts of recommendation systems and like in classes like AML yet. So today is going to be about sort of some of that machinery and prediction, not too much, but sort of how what you're trying to predict is how much will a given user like an item. So you have a bunch of items in your inventory, and what you want to predict is I have some history about the user or some information about the user and items. How do I know? How do I guess at how much the user will like each of the items? I'm going to briefly talk about the problem formulation and some algorithms. I'm not going to go into like the nitty gritty of training them. Like even in the homework, we're going to like train these things for you and just give you sort of the outputs of the prediction algorithms. But I think it's important to understand some of the differences and sort of like some of the assumptions behind the different ways to train them. And we could have like an entire like 1 month on just like training like different algorithms for recommendation systems. And I think some of the suggested readings in the course will point you to those resources. There's a lot of resources out there on this. But like part of training, we're sort of a big part of recommendation systems in practice, but also like how people traditionally teach this stuff is exactly connecting what we just talked about with data collection. Is that there's a lot of differences in sort of the model that you end up training based on what data you end up using. If you use interaction data versus like whether they rated or versus what their actual rating was, all of those things will actually lead to different recommendations in practice. So we'll talk about that a little bit. And then next week, which I think is So in part one, like I said, there's like a lot of resources out there on the internet. There's a lot of other courses that like go far more into detail about what I'm going to talk about today. I'm happy to point to those resources. Part two, which is next week, is I think something that's hopefully more unique to this class, but something that I think is quite undercovered in a lot of data science or machine learning, especially around recommendations, which is, okay, so you have predictions. You have some estimate for how much each person likes each item. Now, like, what do you actually do with those predictions? Like, how do you make decisions on, which items to actually recommend to someone? And we're going to talk about this in the context of, something like Netflix doesn't have capacity constraints. Like everyone in the world can watch the same movie, but a retail setting or basically any setting that's not digital media is going to have capacity constraints, right? You only have 10 of this item in your warehouse. How should that affect your recommendations? We're going to talk about recommendations in two-sided marketplaces. So now, two-sided marketplaces, think like a freelancing platform where workers care about which clients they work for, and clients care about which workers they hire. And sort of just because one side prefers someone on the other side doesn't mean that it's a match the other way. Modern dating apps or modern heterosexual dating apps are a great example of two-sided marketplaces. And so recommendations that you might do in that setting differ a lot from recommendations that you do on Netflix, for example, where the movie doesn't care who watches it. And then we're briefly going to talk about feedback loops and recommendations. So a big part of recommendation systems is, of course, is the data that you're using with it. And so whether you're using explicit or implicit data, the data is being generated based on what movies people end up watching. But if you have a platform like Netflix, the movies that actually any modern large platform, the movies that people end up watching or the things that people end up doing depend on the recommendations they saw last week. And so your recommendations today affect the data that you see tomorrow and the data that you're going to train your recommendation systems on tomorrow. And so that should affect some of the things that you do. Okay. Any questions on the plan? Cool. Okay, so I've said the word recommendation systems quite a bit. I think everyone probably knows what they are, but here's, if you're in the modern online economy, you definitely, you're recommended things all the time. You're recommended shows to watch, items to buy, music to listen to, right? This is the almost the sort of the canonical way that you interact with products on the internet now, right? Because Amazon has millions or billions of items, you can't scroll through all of them. You can't even search for all of them. Amazon is giving you a front page, or Netflix is giving you a front page of things to watch and do. Okay, so how do those recommendations come about? The old school way you could imagine is just like editorial or hand curated, right? Like some expert, some BuzzFeed reporter or whatever, just like compiles a list of their favorite things and then publishes it. And they don't do any personalization. They just send out a list to the internet. You could simply just aggregate, right? So like Netflix can just do, and they do things like, here's what's trending now. Here's the top 10 things people watched in the last week. Now, of course, Netflix is also personalizing that in the background, but and so you could think about just simple aggregates that are just summary statistics of what people are doing and watching without any personalization. But really, the workhorse of the modern online economy is personalized recommendations, where they're trying to say, the world may not care about this item, but we think you will, right? Based on your past history, your past ratings, whatever, right? And this is really the advantage of, and the difference between something like Amazon and something, an offline retailer. So Amazon became famous, or sort of, really became popular in the 90s and early 2000s. They started out as just selling books. And what they did, sort of what their differentiating factor between Amazon and sort of a retail store is, they claim to have every book basically any book in existence. And the way they claimed that is they were lying, in that they didn't physically have every book sitting in some warehouse. But if someone submitted an order for a book they didn't have, they would go out and acquire that book from whatever other place that had it, and then they would ship it to their customer, right? They didn't actually store all the books that they claimed to have in their catalog. And so that's, if you're a book collector, you're looking for rare books, that's extremely valuable. That's a very valuable service. But at the same time, that also means that now their catalog is just way bigger than anyone else. And if you have that big of a catalog, different people are going to like different things, and not everyone's going to know no one's going to read the entire millions of things on the catalog. And so really you need personalized recommendations to say, or you have a search bar, but also have personalized recommendations for, we think you're going to like these 10 items out of our millions of things in the catalog. And that's what we're going to talk about today in detail. Okay, so the motivation is to filter the huge content I have to be more relevant to each user. We use data inferred from signals. You can use either direct or explicit data. You can use indirect data. And then what's the intermediate goal? The intermediate goal is to predict the relevance of each item for each user, right? I say intermediate because that's actually not your goal in any online setting, right? You never only care about prediction. You always care about, what am I going to do with the prediction? But that's going to be sort of the intermediate goal that we're going to focus on today, is just the prediction aspect. Okay, any questions here? Yeah, so the question is how does search play into this? As you could think about search versus recommendation. So in some sense, you can think about sort of the output of search as a recommendation, in that in personalized recommendation, what we care about is we want to just show you 20 items based on who your history, who you are, or whatever. Search you can think about as, every place, Google certainly personalizes your search, the output of the search. And you can think about that as they're the 20 URLs they show you is sort of the recommendation based on your context. So the context being the thing that you typed into the search bar, and but also sort of your individual history, right? So for example, one of the conferences in my field is called the Web and Internet Economics, which has the terrible acronym WINE. But if I Google wine, I get results for that conference and not wine, right? And so in that sense, that's also a personalized recommendation system. It's just something that's also using the context that I gave it. Okay. So what's the formal model? Let's say that I have some set of users, X, and some set of items, S. Today, I'm going to sort of pretend that one side is only one side is people, and so I'm going to call that side users. The other side is items. But next week, talk about two-sided recommendations. We can think about both sides being users of different kinds. But yeah, so for now, let's say that we have users and items. And each user, and so sort of each user has a preference for each item, right? So you could think about there's being some function u that takes in, the like a specific user and a specific item and maps that to some rating from like 0 to 5, 0 to 1, or whatever. And so R is just like a giant matrix of ratings that this is what the rating that a user would give an item if they watched it or if they consumed it or if they knew it existed. And we're just kind of, what I'm about to say should trigger some things or back to measurement theory, but for this, we're just going to assume that R is the rating is 0 to 5 stars or 0 to 1. It's just some single dimensional ordered number that's bounded. So the way I want you to visualize this throughout this section is suppose we have sort of I want you to visualize a matrix like this, where the rows can be the users, for example, and the columns can be the items. And I have some historical data. I'll talk about where that could come from in a second, but let's say I have some historical data that maps historical ratings. So this could be based on your view history or your ratings or whatever. And some of these numbers are filled in because of the history. Now, in reality, the vast majority of these numbers are missing, right? Alice has never interacted with most of the millions of movies in the database. Has only interacted with 1% or less than 1%. So I have some of the entries, but most of the entries are missing. And the goal for the prediction part of recommendation systems is to fill in the missing entries. And you can think about whatever metric that you can think about mean squared error or whatever prediction metric you might be learning in applied machine learning. Any questions here on the challenge? Okay, so what are the 2 steps to do this? The first step is, in the last slide, I just assumed that you have this matrix R hat of past data, but you don't have that's also a choice to make. Is what's going to be the data matrix that you use for the existing signal, for the existing ratings. And so step 1 is to create a matrix like that. And then the step 2 is to fill in the missing entries, right? So it's sort of that should be, and I say that these are distinct because step 1 in some sense really defines your goal, right? And we're going to have you play around with this a little bit in the homework, where if step 1 is just a binary matrix of what I've watched in the past, then the sort of filling in the missing entries is in some sense a prediction for what am I going to watch in the future. If the past data is rating 0 to 5 or whether I binge the show or something, then the prediction that I'm doing is now predicting if I were to rate this or if I were to watch this, will I binge it, right? And so oftentimes if you look at these other machine the sort of the other recommendation literature out there, classes at least, they often sweep this under the rug that the actual prediction problem you're solving changes with different data that you're using. And then, whatever data that you end up using, the machinery to fill in the missing entries tends to be the same. Okay, so let's very briefly talk about step 1. I don't want to belabor this point because I think y'all get it from the entire data collection module that we just had. So, you could use explicit data. You could just ask people what they think. The challenge, of course, is all the opinion collection stuff that we just finished talking about. On Netflix nowadays, no one answers poll, no one gives ratings. Netflix has very heavily de-emphasized ratings. On most product pages on eBay, very few people are actually submitting any ratings nowadays. And who is submitting is like a biased sample of the population that bought an item. For example, people with on Amazon, maybe people with negative ratings are the ones submitting more than someone who just thought it was like average. Maybe on Amazon, people who received coupons as a discount in order to induce them to rate are the ones who are rating more than other people, right? So you have all of these challenges. You have the measurement error that like, what does a 1 to 5 scale mean for like how much like I enjoyed watching this movie? And then you have like consistency issues, right? So like just basically everything that we just finished talking about. Okay, so in practice, in a lot of especially digital media, basically no one is using explicit data anymore. Even like 7 years ago, like Netflix had like they still had the 5-star, they still had this like all these systems that you could give them, and like they emphasized it in the user interface, but like they were not really using it in the back end. And like at this point in 2021, they've just like de-emphasized it even from the user interface. Okay, so alternatively, they use implicit data, which is just a lot of different data that you have on people's opinions, right? So does someone finish watching the show? Do they watch the next episode? Do they keep coming back to your website and buying other things, right? If someone had a terrible first experience on eBay, maybe they didn't submit a rating for that seller, but they just never bought on eBay again. Do you like keep browsing other, right? Like, do you like see the item and then decide you don't want to buy it and like keep browsing for other items, right? So like in Google, for example, one of the like the key metrics, you were talking about search. So one of the key metrics for search is like that you can evaluate the output is like if I search something, do I click on the first link or do I like type something else in the search bar? And if I'm typing something else in the search bar, that's telling Google that the first page at least was like not what I was looking for. Right. So one key thing is like that we leverage in the paper mine is, for example, like do they rehire the same freelancer on freelancing marketplaces? Right. Like I worked with someone, I like what they did. Do I hire them again for a similar job in the future? And what I want to emphasize here is that this is not just more data than explicit ratings. This is like fundamentally like sort of each of these things are telling you something different than explicit ratings tell you, and that they tell that like that each other tells. Right. So it's from a different population of users. You have implicit data, sort of some kinds of implicit data on basically all users. Right. If you think about binary interactions, did I watch this movie on Netflix? Did I like shelve this movie on Goodreads or whatever? You have that matrix for literally every user, right? Because either they did it or they didn't. But if you think about, did I continue watching this episode? You only have that data available for people who started watching the episode, right? Like that data is neither 0 or 1 for people who didn't watch that episode. It's like it's missing, and you should treat it as missing in your prediction, like in your prediction task. You can't like sort of in the completion task, how you use that as training data really matters, right? So it's often more numerous, but it's often harder to analyze because it's harder to intuitively think about like how that maps to something you care about. So if someone is binging a show, does that mean that they're just like watching it on the background while doing a bunch of other tasks, or does that mean that they like really really love the show, right? For the same people at different times or for different people, the same actions can mean very different things about like what they feel and like what they believe. On the other hand, economists love this phrase revealed preference, which is the idea that what you do is sort of more informative about your beliefs, about your preferences than what you say, right? So even if I like give something a 1 star, but I keep binging the show, that means that that's far more like the fact that I'm watching it is far more predictive of what I'm going to do tomorrow and what other shows I'm going to watch than like what I say. Okay. So you can use this data in several ways. You can try to combine all these different interaction signals that you have into just one matrix and like do some weighted average, for example, and then you can do prediction that way. You can also train different models to predict different behavior, right? So you can have one matrix that's just like the interaction matrix, did I watch it, and use that for recommendations on one part of your system, like for recommendations on the front page. And then you can maybe train a different signal for like just on data, did I like continue binge watching something? And then you can use that for like an estimate for how much I'm going to like it after I click on it, right? So you can use this in many ways. You can combine it. You can train different models. Something that there's like increasing concern about, but I just want you to be aware of, we're not going to touch too much upon this, is this worry that using implicit data takes away user agency, right? So I think psychologists, I'm going to mess up the term. I think it's like there's this like difference between first order desires and second order desires, where maybe like I can't resist like binge watching like a trashy reality show on Netflix, but like what I really want to be doing is like watching like nature documentaries, right? If you like told me what like I wanted to watch was like nature documentaries, but like Netflix shows up and I instead like click on like a trashy reality show, right? And so if Netflix is just using my past history, it's going to keep recommending me things that like I like don't want and some like I don't want to want. And so the question is like, is that what you're fueling when you're using implicit data? And so in different settings, this might be something that you think about is like, what is the goal of the recommendation system? Is it to just like increase user engagement in the short run? Is it to like make users happy in some sense over the long run, or so on? Okay, any questions about step one, which is just like, and we're going to explore some of these things a lot more in the homework, but like I don't want to belabor this point too much just because we finished an entire module on this.
Is there an assumption that a user is just one person? Like, if multiple people are watching the same Netflix account, or you have an Amazon, multiple family members use it, so like an assumption that just don't believe that happens, or can you build a model if multiple people are using it?
Yeah. So the question is there an assumption that a user in this sense is just one person, or if like people are sharing Amazon accounts, there are multiple people, or Netflix accounts? So that's a good question, and that's actually one of the core challenges in like modern advertising, which is people share devices in a family, and if a teenager is using a device, you want to do very different advertisements than if their parents are using that device. And in like a lot of these like enclosed platforms like Netflix or Amazon, they have some advantage that they can, in some sense, figure out. Like they have other context signals to figure out either which user it is, or like whichever user it is, this is like what they currently care about. So Netflix, Spotify, a lot of these places have user profiles for that reason, right? They just like ask you to tell them who it is, and then they'll tailor to that profile. They also, if I don't know how much Amazon prefers this, but like, a lot of families share Amazon accounts across different like states or cities or whatever, right? Like I have, whatever, 4 or 5 people sharing my Amazon accounts, and we all live in different cities, right? So like Amazon can, I'm not sure if they are, but they could easily just like use your IP address to figure out where you are, and then figure out who you like, which one of the accounts you are, and then use like do recommendations based on that. So yes, and that does matter, but there's also, and like at least in closed platforms like Netflix or Amazon, they have ways to get around it. In open platforms or just like random advertising on the internet, this disambiguation is like a hard challenge, and it's like a big reason why like a lot of modern advertising is just like for all the hype about personalized advertising, it's like why it supposedly doesn't really work that well. Any other questions? Okay. Okay, so let's move on to, I think, sort of for most of this lecture, we're going to be talking about various ways to do step 2, which is, so what step 2 is, you have this matrix and you want to fill in the missing entries. Okay, so I'm just going to walk through a few potential strategies to do this. I'm going to sort of simultaneously try to go slowly, but also, like I said, there's like entire like months that we could do on teaching like the machinery on actually how to train some of these things. We're not going to talk about like actually training these things today. I just want you to understand what are like the different assumptions and the different like implications of using these different types of recommendation systems. Yeah, so the question is can I just explain what these values represent? So for this step, I want to be like vague on what the values represent. In that, so you have rows of users. So like Alice is this row, Bob is this row, Carol is this row, David's that row, and then you have columns of items like Avatar, Lord of the Rings, and so on. And the entries represent, in some vague sense, how much Alice, like sort of the top left represents how much Alice likes Avatar on a scale from 0 to 1. The 0.2 represents how much Alice likes the matrix. And this could be filled in from whatever explicit or implicit ratings or whatever signals that you have in the past. And then the goal is like, Lord of the Rings is missing here. And let's suppose I get more data and like that entry appears. Like, what is that entry likely to be, right? Does Alice, based on what you know about Alice from the matrix, from like the ratings from Avatar and the Matrix, are they likely to like Lord of the Rings? Right, and so that's the task, is to try to sort of predict what all of these missing entries are going to be. So you could think about it as like, let's suppose these were explicit ratings where you asked to rate each item from 0 to 1. If I asked Alice to watch Lord of the Rings, what would they rate Lord of the Rings? Now that, something that I want you to think about is like, sort of the question I just asked is a little undefined. Does that mean if like Alice like chose to watch Lord of the Rings and then rated it, or if I sat them down and like strapped them to a chair and forced them to watch Lord of the Rings, what would they rate it? Right? Like these are all different things. But yeah, so I want to abstract away from all of that, where the goal here is just to predict the missing entries. Any questions? Okay. Okay, so what are some possible strategies to do this? The first one I'm going to call content-based recommendations, which means that you use existing data on the items to group together similar items. So you use data like genre, who the director was, who the actors were, what year it came out, right? So like these are all like data that you can download from IMDb, or if you're a retailer, you have like metadata about each item, right? For clothing, you have like color, style, blah, blah, like designer, all sorts of things. And then all you do is, yeah, okay, so I'm going to talk about this in detail. But okay, so one, you have content-based recommendations where you group together similar items. And then you have user-based recommendations where you do the same thing, but you group together similar users. And so you just say this user is similar to that user, they probably have similar taste. And then really the workhorse, I'm going to say modern, but like not anymore, because like replaced by like deep learning techniques for like, in large platforms, but definitely still the workhorse in medium-sized places is a technique called matrix factorization, which is like an automated way to find the dimensions that matter. So in like content and user-based recommendations, I'm going to go into this in a little bit more detail, but like in content and user-based recommendations, you like group together users and items based on like dimensions that you see, right? So like genre, age, ethnicity, director, actor, whatever. But it might not, like, those dimensions may not matter for whether someone likes a movie. And so matrix factorization based techniques are try to like find an automated way to like find the dimensions that matter. And that's really, for those of you who've heard of like the Netflix prize, this is a technique that I don't want to say like came out of that contest, but it like really popularized by that context. So so for those of you who don't know, this was a long time ago. I think in 2008, something along these lines, Netflix announced, I believe, $1 million prize for sort of anyone who can improve upon their internal rating system by at least 10%. And they released a bunch of data on users and like past, like, I think, explicit ratings, and they said, anyone, they just like announced an open contest. And people very quickly realized that like their existing rating system sucked. So just like taking the mean rating for each movie and the mean like rating that each user gave all the movies they saw got to within like 3% of like the system that Netflix was actually using, and like doing some weighted average of those two numbers, right? But it actually took, I think, a long time, like a few years, to like beat upon that system by at least 10%. And a lot of the systems that got close used just matrix factorization. The system that ended up winning used like a weighted average of like 50 different systems. Sorry, that was a tangent, but okay. So anyway, we're going to talk about these three types of recommendation systems. Okay, so let's start with content-based recommendation. The main idea is to recommend items to you have some customer, user X, you want to recommend them items similar to the items that they've liked in the past. That sounds like a great idea. And this is, and I've already given some of these examples. So for like movies, like, so okay, so it sounds like a simple idea. Like the hard part here is like defining similar, right? Like what makes item A similar to item B? If you, if you're at a place that has a catalog of 10 items, maybe you as an expert can just like handpick the similarity of like, this 10 by 10 matrix of how similar each item is to every other item. But, for something like Amazon, which has like millions or billions of items, how do you just find the similarity between each pair of items? But okay, let's suppose, yeah. And so, but then the idea is once you have that similarity between every pair of items, I just recommend to the user items similar to the items that they've liked in the past. And here, sort of the key for content-based recommendations, how we define it, we're going to talk about it, is you define similarity based on like known dimensions that you have. So actors, director, genre, similar content, author, so on, right? So you just define a vector for like on data, like metadata that you have about each item, and and then you just do similarity based on this vector. And so and then you just fill in the entries based on how like similar items. So again, okay, so once you have this matrix of like how similar each item is to every other item, there's like many different ways you can think about filling the entries once you have that. Here, just for explanatory purposes, I'm going to pretend that pretend that we used k nearest neighbors, where k equals 1 here. So for each item, I'm just going to find the other the most similar item, and just pretend that those two sort of ratings transfer across those two. I think applied machine learning, the ML course has covered k nearest neighbors by now. Yeah. Okay. Great. Okay. So, and if you don't know what that is, it's sort of my explanation just now didn't make it clear. Please raise your hand and ask a question. Okay. So what would k nearest neighbors here look like? So let's pretend amongst these 4 movies, Avatar and Lord of the Rings are the most similar. They're adventure of some kind in the new world. I don't know. But so if we pretend Avatar and Lord of the Rings are the most similar items to each other, then you just fill in your missing entries based on if Alice has liked Avatar, give a 1 to Avatar, then you pretend that she'll give a 1 to Lord of the Rings. Bob, rated Lord of the Rings 0.5, you can give, and pretend that he'll give Avatar 0.5, and then so on. Right. So you just look at the columns, and you just fill in the entries by finding similar columns to each other. Any questions about the mechanics here? Okay, and you could imagine, I give a very trivial way to do this with k equals 1 nearest neighbor. You could imagine all sorts of fancy things here. You could, find the 10 most similar items and they do a weighted average based on how similar they are, right? You can do all sorts of fancy things. But the key here for content-based is for each user, I'm not looking at any data by any other user. I'm just saying for that user, what did they give rating, which items did they give ratings to? And then how can I use those ratings to see how they'll like other items? Okay, so what are some pros and cons of this approach? What's really nice is that you don't need any data from other users, right? So in this content-based approach, the only thing that I use for Alice's predictions are Alice's past history. And so what that means is if I have a new item, I don't need a lot of other users to have consumed that item before. I can just be a new item comes into my catalog, I can define its distance to every other item, and then I can immediately do predictions. You can also provide explanations. So, for example, for those of you who have Netflix or a lot of digital media, they provide explanations for why they say you're going to like something, right? They'll have a title, because you liked XYZ or because you like romantic comedies, and then they'll give you 10 movies, right? So that's really easy to do in a content-based recommendation system because you know that Avatar and Lord of the Rings are close by because they're both adventure movies or something, right? Or these two things are similar because they have the same actors or the same director or the writer. On the other hand, actually defining this distance function tends to be a really hard thing to do in practice, right? How do you know what matters for whether someone's going to like something, right? Is the fact that they have the same director really a great indicator that they're going to share preferences if that director is moving across genres, or that one type of just because someone likes one children's movie that they're going to like another children's movie or so on, right? So these are all assumptions that you have to make, and this is not doing that in a data-driven way, right? This is imposing a structure because you're imposing a distance metric based on the vector of features. This also struggles to find recommendations for new users, right? So it was good at what's called the cold start for new items. You can immediately provide recommendations, but for new users, you can't, right? If a new user comes in and has never rated anything on the platform, then there's nothing you can transfer for that user. Any questions about content-based recommendations? Okay. Oh, there's one more. Okay. You have what's again, this is like an increasing worry as like recommendation systems go everywhere. You can think about them as filter bubbles or over specialization or whatever, which is this is never going to recommend like a totally new item to. And actually, this is an issue with all three approaches that I'm going to talk about today. And actually, it's an issue with like accuracy predictive based recommendation system in general, is that you're never going to be able to recommend like truly new items to people, right? I'm only going to recommend, or I'm only going to predict that you like things that you've liked in the past. Like I'm never going to predict that like this completely new thing that you're going to like. Now, I do want to distinguish between like, just because it never predicts that you're going to like this completely new item, it's your choice as the algorithm designer to recommend it anyway, right? So the system will never, I'm using these slides from someone else, but so they, and I think this is like, the conflation that a lot of people while teaching recommendation systems do is there's a difference between prediction and recommendation, right? Content-based prediction is never going to predict that you like a new item. But you as the recommendation system designer can choose to recommend like a poorly predicted item anyway. But yeah, the system will never predict that you like truly new items. Okay, so user-based similarity is basically the exact same thing, but now you clump users based on like characteristics that you have in the past. So something, like age, ethnicity, demographics, location. If you have, if the recommendation system is online, then you have like their cookies on their internet. So you have, you can build like a fairly sophisticated user profile based on their cookies, right? But you do essentially exactly the same thing, but now in rows instead of columns, where let's say for whatever reason, I've determined that Alice and Bob are similar. Then I can just fill in the missing entries for Bob based on what Alice likes. So we don't have the entry of 1 for avatar for Bob, and so, or we don't have an entry for avatar for Bob, and so we just fill in a 1 from Alice. And then we can, do the same thing throughout, and then there's all the same fancy stuff that we can do for user-based similarity as we can do for item-based similarity. Any questions? Okay, so the pros and cons are now very similar to the item-based similarity, but now they're just like transposed to some things are now better for users, but worse for items and so on, right? So now this works for any kind of item, right? Where you don't need to do any feature selection. You don't need to know that movies, that preferences for movies are shared across directors or across actors or genres, right? Because you're making no assumption on like distances between movies or differences between items. But now you have a cold start problem for new items. So a new item comes in, if no one's seen it before, then you can't transfer any ratings across users. Yeah, and this is also called the first rater item, which is you can't recommend an item that has never been previously rated, right? So like, how does an item get its first recommendation or first rating? This also has this is something that didn't have an equivalent on the item side, but it's what's called popularity bias, which is now this sort of systems, user similarity-based system, tends to basically just recommend popular items. And so maybe if we scroll back, we can see why. If an item is filled in for a lot of people, So I guess in this example, every item is filled in for exactly 2 people. But let's pretend that everyone in the world has seen The Matrix, but maybe fewer people have seen Pirates of the Caribbean, right? Then, like, as soon as I define similar people, like for like there will always be for like Bob hasn't seen The Matrix, but like almost surely the most similar person to Bob or the most 5 similar people to Bob, like a few of them have seen The Matrix, and so you can fill in that entry. But if you have a movie that basically no one has seen, so let's pretend Pirates of the Caribbean, terrible movie. I don't know why people like it, but like let's pretend no one has seen it. Then like the most similar people to Bob are unlikely to have seen it, so you can unlikely to have fill in that entry, right? And so this tends to favor popular items over unpopular items, which might not be a bad thing, but it is a thing. Okay. And similarly, you're similar to weighting, or what I talked about then, is you are like you're stereotyping people on the distance metric that you defined, right? You're you know in content base you were doing that for items. Now you're doing it for users. Now you're imposing onto like your system that people of the same age or ethnicity or location or gender or whatever will tend to have similar preferences for items. And so if someone has, so that's like stereotyping. And if someone has unique preferences, then that's not going to be reflected in user similarity-based recommendations. Yeah, so great question. So the question is like once a new user item comes in and you fill in the blank spaces, then like do you ever update those? So in practice, like I like put this matrix up and I say you like fill in the entries, but in practice you almost never like you don't actually ever have like a matrix sitting somewhere in a database with like every entry, because that would be huge. That would be an absolutely huge matrix, right? Like you would have like millions or billions of users and millions or billions of items. And so that's like a million squared or a billion squared number of entries, right? And so just like storing that and processing that is like something you don't want to do. So like it's like a misnomer, or I don't know, misnomer is not the right word. It's a mistake to think that like that thing is ever stored, but rather you could like think about that you could generate those things like very quickly through like if a specific user comes in and you want to do recommendations for them, then you can like very quickly generate sort of like predictions for just them. Maybe not for all items, but for like a subset of items that match their like search, or like a subset of like the top 500,000 items that you thought they would like in the past, right? And so if you're doing that regeneration every time, then like that sort of solves this like static question. Yeah, so the question is do we like ever combine different types of models? And like certainly, right? So like I'm like teaching these as like distinct models, but in practice you have like many different kinds of like sort of you'll combine user-based, similarity-based, matrix factorization-based that I'm going to talk about next, and sort of like I was saying earlier, the eventual winner of the Netflix prize actually combined like 20 or 30, or I forget, it was either 20 or 30 or like hundreds of like different recommendation systems, and then did sort of a weighted average of like all of those predictions into its final prediction. Yeah. And in the homework, I'm going to actually ask you to like do sort of something along these lines, where sort of combine it in a certain way where we use sort of stepping back. So one reason why you would want to combine it is these different systems have different strengths and weaknesses, right? So for a content-based recommendation, it's really good for a new item, but it's not so great for a new user. For user similarity-based recommendations, it's good for a new user, but not great for a new item. Matrix factorization is not good for either new users or new items, but it has other great, like it's really, really good for existing users and items. And so in the homework, I'll first ask you to not train, because we'll just give you the sort of the trained matrix, but sort of or like the trained output for matrix factorization. So I'll first have you do give you sort of have you use matrix factorization based recommendation, and then think about how you would use user similarity based recommendation on top of it to like deal with new users. Any other questions? Okay. Okay, so in the last 10 or 11 minutes, hopefully I'll get through most of matrix factorization, but it's fine. We'll just pick up on Wednesday if I don't. Okay, so what is matrix factorization or latent-based models? In the content or similarity-based approaches, what they shared was you assumed you knew how items are related to each other, right? So like you assumed you could create. Sorry. Okay, that's not going to work. Okay. Just wait. You assumed you knew that like you could create a distance metric based on genre or demographics or whatever. And you assumed that like ratings or like what people like are related to those distance metrics. But that's like in practice really hard to do, right? Okay, so yeah, so in that sense, you had items that are represented by a vector of characteristics like genres, users by a vector of like demographics, location, internet history, whatever. And what you assumed was that like people's preferences were related to those features in a way that you could understand and code up in a distance function, right? So you could code up like a distance function that people who are the same age are like, like it's being the same age is 5 times more important than being in the same state for like what your preferences are. And that's just like not an assumption that you want to be making in a lot of places, right? Because preferences are complicated. They're based on subtle things. They might be completely unrelated to these demographics, or they might be related to these characteristics, but in ways that you don't understand. And so the idea for latent factor-based models or matrix factorization-based models is why don't you learn vectors for each user and item from the histories you have for that user and item, right? So like, why don't I learn, so instead of a 10-dimensional vector for someone defined by their age, ethnicity, location, internet history, why not just learn a 10-dimensional vector based on their prior ratings history? In reality, not 10, more like hundreds, but sure. Okay, so what's the task? Now you're going to learn a user vector, UI, in D dimensions. And so this just means UI is a vector on the 10-dimensional real, like, it's a 10-dimensional real vector. And then you also learn a D-dimensional vector for each item. Yeah, so the question is are the vectors going to be constantly changing in dynamic? And yes, right? So in practice, you're going to be like relearning, like retraining these things quite often. And there's all sorts of like nice tricks to iteratively relearn things as opposed to like training on the entire history every time. Not going to cover those in this class, but yes. Okay, yeah, so you learn a vector for each user and each item. And you want to learn those vectors such that for every pair of item and user, so for each item I and each user I and each item j, the dot product of ui and vj is approximately the rating that you have in your matrix, right? So you predict, so you learn these vectors such that you can recover the ratings matrix that you have. Okay, and so now I'm going to hand wave away training these things. Even in the homework, I'm not going to ask you to train these things. I'm just going to give you outputs. I think I shared one book on like talking about how to train this. I'm happy to share a lot more resources if that's what you're interested in. I think AML might cover this a little bit. I'm not sure. But yes, there's a lot of tricks, a lot of subtleties to actually train these things. I don't want to cover those in this class. It's not the core of this class. But yes, okay, so suppose you've trained these things. Now you take the dot, so, such that in the history that you have, these vectors are predictive of the ratings that you have. And then for every pair of users and items that you haven't seen, so for all the missing entries in the table, you just predict that the rating is the dot product of the user vector and the item vector. And for those of you with maybe a little bit of linear algebra background, you could think of this as factorizing the matrix, where suppose, so this is the ratings matrix that I had earlier. Suppose the ratings matrix was of rank D. I'm not sure how. I'm happy to discuss this in more detail and explain these things, but I'm just trying to provide some intuition for people with the linear algebra background. So suppose your matrix had some rank D. Then we know that we can factorize that matrix by using singular value decomposition into so you have U users and I items now. And if this matrix is rank D, then we know that we can factorize this matrix such that it's U times D. And so these times something that's D times I, right? And then what you can get is, what you end up getting is a D-dimensional vector for each user and a D-dimensional vector for each item. And so if you have a ratings matrix that is of rank D, and you have all of the entire matrix is filled in, then you could actually you could recover these factors such that you could perfectly make the entire matrix from D dimensions for each user and each item. And this is just trying to apply that idea by where, in practice, this matrix is not going to be D-dimensional. It's going to be super high dimensional. It might approximately be D-dimensional. And then, of course, in practice, you have a bunch of missing entries. And so because of the missing entries, you might not be able to exactly without noise recover the singular vectors. Great question. So the question is qualitatively, what do these dimensions stand for? And that's what I'm going to talk about on the next slide. The key weakness for this or one of the key weaknesses for this technique is for similarity or for user or content-based similarity metrics, you knew that this was recommended because this dimension, because these two things are close in genre. Now, in at least when you just train these things, you're training this in a completely black box way. Without further work, you don't know what the dimensions stand for, right? You don't know if the first dimension is some children's movie, this is a children's movie, or the second dimension is that. And it's almost worse because with the matrix, or with vectors, it doesn't even make sense to say something like the first dimension or the second dimension, right? You can rotate a vector, if I just multiply every vector by like a matrix that that sums up to 1, then like I've like rotated the vector, and so what used to be the first dimension is now like a linear combination of the second and third dimension, or the first and second dimension, or whatever. And so interpreting these things is a challenge.
Would you like group dimensions, like do like k nearest neighbor on the values of dimension and see like, oh, like this dimension's got like 0.5, 0.4 for these different types of users. We could say like these users are being grouped together and assume because that's like try to make sense.
Yeah, so the question is can you try to make sense of the dimensions? And there's a lot of work in sort of machine learning right now on exactly this question, on how do you extract explanations from like these like what are called latent factor or embedding based models. And there's like certain tricks you can use. And so for example, like the like one trick you can use is literally like the eyeball trick. And so suppose I trained something with d equals 2. And then I just like, if it's two-dimensional, then every movie here is just has a first dimension and a second dimension. And so you can just plot it like on paper. And then you can just like eyeball it. And so for here, if you like have I don't know if y'all can see this from back there, but like if you just like plot these things and then you eyeball it, then you can like kind of guess that the first dimension is children to adult movie and the second dimension is like a blockbuster popular movie versus like an artsy movie, right? Now, I mean, now this is like in practice, you're never going to get something this nice. So like it could be like rotated by, right? Like this entire thing could be rotated 45 degrees, or like 2 dimensions almost never come out this nicely. But yes, there's a lot of work on trying to recover dimensions. And so, for example, some work that I've done in the past with natural language processing is you can like sort of the trick you can use is like you can like find a bundle of vectors that like relate to the same like construct that you care about. So like if like the construct you care about is like gender or something, then you can like, or if the construct that you care about is like some binarized version of gender, then you can like create a bundle of vectors that like relate to like women and men respectively. And then you can like create the average vector within each bundle. And then you can project every other word onto that dimension, right? Onto like sort of the dimensions defined by those two sets of vectors, right? So there's a lot of tricks to try to extract explanations out of it. Okay, so I think that's all. I'll finish up here. That's all the time we have today. So I want to end up with some announcements. Okay.